Hello and welcome back. So let's move to the next video. So we worked in the previous one the rectangular wind. So now let me show you the tapered wind, but the concepts are the same. The important thing is that recall from the review, but also from the lectures now from Professor Botaro, there are this very interesting graphic. Now this is a theoretical result, but also experimental one regarding the tapered ratio. Okay, so what we have here is the influence, okay, a combination of aspect ratio, different aspect ratios, and different tapered ratios. And you see the induced drag parameter. Recall that this one is related to the induced drag. You have it here. So we want to have a low value. Here clearly you see the influence of tapered ratio on this parameter, and see that the minimum value is something about 0.4, 0.3, maybe 0.45, 0.5. There is where you have the value. So this is already a theoretical result that we can use as a starting point, but also as a final design. It's already known that this is the ideal tapered ratio. Here also you have it for the slope parameter. It's the same concept, probably a little bit shifted to 0 to the left, but see there's something about 0.3, 0.5. So there is no need to use fantasy and start to go with really low taper ratios, or to use the rectangular wing, because it's not the ideal one. See that it have a large induced drag factor. So if we add a taper ratio, something about 0.4, okay, already is going to give us very good results. It might happen in this case that the stall pattern might be closer to the tip, but that we know we can control it with twist. And just by adding this taper ratio and twist, we can get very close to the elliptical distribution. And you will see that only in few iterations. Here in the wind, we created another section, we add many things here. Already this result will be something close to the elliptical distribution. And to point out that there is no need to play around with this one or using crazy values. So if we go here, you recall this review, here you have many airplanes, and as you look at all these airplanes, you will see that the ratio between the root and the tip is something about 0.4, 0.3, 0.5. All of them checkable except for the delta wind, that the taper ratio is 0. But see that all of them already have that taper ratio. So that is a result very well known. Okay, so go your wind, and if you want to add taper ratio, 0.4 is already a good value. Probably you can iterate 0.3, 0.4, 0.5. That's all. And see that this wind, which is a wind with taper, trapezoidal wind, is already similar to this one. And if you want to get the elliptical wind, it's like a tapered wind, but you need to add many sections in XFLR5 to approximate this one. But already this is a very good one. So I think these are my two favorite airplanes, all airplanes. This is the P51 Mustang. This is the first one that use a laminar flow wind, and this is the Spitfire, that they exploit all this concept of the elliptical lift distribution. Beautiful airplanes. So now let's do the design. So I close the software. Okay, I save my file there. Remember to save the file, because for your homework you need to send me that file. So I will launch XFLR5, okay, and let's design the wing. So I will start model, and I will go directly now to the direct analysis of the airfoil to this. So I will choose any standard airfoil. Let me choose, I don't know, 2415. Okay, I will use this airfoil. Okay, save. Okay, every now and then save. I save it there, and we have the airfoil, and now we don't know the velocity, nothing. And let me go and move to wind and plane design, and let's design the wind. You go plane, define a new plane. I don't want fin, I don't want elevator, I just focus in the wind. And see, by default, always the center of gravity is 0, 0. Okay, now this is how you shift it, but always by default center of gravity 0, 0. And you can change it in the definition of the analysis. Now you click in define and you enter into wind design. And here you can design your standard wind. So I will put any values here. Okay, so I recall the rectangular wind was 4.6 now, the one that the example. So I will put here 5. Okay, and then the core, or let me put this one 1.2. 1.2 here, and let me put here 0.8. So when you design, always check that this one is giving you the all the quantities. So see that we have a taper ratio of 0.67. Let me reduce that to 0.4. Okay, too low. 0.5. We have this taper ratio, and this is already an okay wind. Then, if you want to change now the sweep angle of the leading edge is here. So if you put it here, you have this straight wind. So this is already a good wind. Okay, many airplanes use something like that. So you want to add a little bit. Probably this is more visual than the actual effect on the wind. You go here and you add your offset. So you go here 0.5 and you put it there. So you do your geometries. You have something perfectly symmetric. So I will put there 0.4. I will put here 0.3. So see that I have my tapered wind. I will add the airfoil, the one I created there. So you have seen how to add also the twist, geometrical twist, aerodynamic twist, whatever. So let me add a little bit twist, 1, -1, and voila. There you go. So if you want to add another section, just put it here, insert section. And for instance, you want to approximate, see that now I added many sections. As you want to approximate that elliptical, you just need to do your algebra and your ellipses, and then you get the radius there, the diameters, and you design your wind. Okay, it's up to you. So you can add as many sections as you like. So I will leave it like this, just 2 sections. And this is already a very good wind. Okay, probably I can criticize a lot the airfoil. It's not the best airfoil. And this is it. Wind with tapered ratio, save here. You want to rename, so see that default name. I want to change this name and I want to call it here, rename, I don't know, Taper 1. We have it there, Taper 1, save your project. Okay, we go analysis, and we can run the analysis. And let's say that I want to run this analysis at 50 meters per second. It's already telling me here, these are the Reynolds numbers. So see that now in the previous one, rectangular wind is one Reynolds number. But here, as you have different cores, each one will see a different Reynolds. So now you need to run, if you want to run the viscous case, you need to run for all these Reynolds numbers. Okay, so save. If I try to run a sequence, instead it will tell me that everything is outside this law because I don't have that data. So I need to interpolate all those values. So always here, well, you can do this computation manually. Or just look at here. So we need to run a lot of Reynolds numbers. So to do that, you go back to full analysis, and you can do it manually, or you can go batch analysis and just put your Reynolds numbers here. So let me go. So this is something that we need to, I hate this part, but should be something automatically that you feel, but we need to do it manually. So, and always remember, I recommend you to do these increments at 100,000. Okay, and let's wait a little bit while I fill in this, and see you later. Okay, I'm back. So see that I populated my list from 1.5 million to 4.5. It's something that you need to do manually. Probably there is a way to do it automatically. I haven't seen that one, but remember, if you want to add a new value here, you click in the ellipses here, and after, and then you can enable, disable. So it's not enabled, click here, the X, and if you want to erase, so you add your values in that way. So see that I added all my values, and I'm ready to run. So it's going to run parallels. All these Reynolds numbers, all these values. Okay, before running, let me save it first. Who knows, probably crash. Go back here. The information is still there. You can lose it. Analyze and see what happens. So it's running. See that all Reynolds number, all this angle of attack. So it's a lot of information that we need. Okay, and at this point, okay, it still is running. Okay. Bam, bam, bam. So yes, analysis complete, and we're done. So we have all these Reynolds. We cover probably this one. I don't need it. I can erase it. Save. We cover everything, and now I can go back when I'm playing analysis. See that I'm sure that those values are covered. Save, and we can do the computation analysis, and there you go. See, very simple, easy peasy. Okay, so it doesn't matter the airplane, whatever we're doing here. So see that this one in this condition for this velocity is generated. So let's say that my goal is 4,000 newtons of lift. So you see that here you have the trim condition. Look at that, this wing have better properties than the previous one. Adding the taper, see that I have better properties. Okay, so I'll have that influence there. Here you have your drag, your LD. So we go here and we're interested in this. So if we check the induced angle, so click here, press R to zoom this. Here we start to see the difference. So by adding that taper ratio and the twist, look at that, we have this. But I want to see that we're controlling the angle at this local lift. And this is what we have. So probably we added too much lift, or probably would be better. So these are the steps. So what I'm showing you, I think you should follow that also for your win. The most critical thing, as you can guess, will be the airfoil selection. So probably we can add a section at 2 and probably one at 4, or remove the twist, the geometrical twist. So if I go back, plane here, just the wing, and let's say that this was too much, probably let me put it at 0, save, okay, and select here, analyze. Okay, so probably this is asking me to add maybe something here at 3. So if I go back, when let me add a new section, so put it here, after, and I put it at 3, and that one it will require a little bit higher, so let me put 6. Okay, select, analyze, and see that already, see the effect there. And go back, now I go back here, and this one, let me put it constant there. So the intersection, it is constant, and then here I add this one to avoid having now here this stall in that section. I'll see that it's getting better. So maybe I can add a little bit more at the root or some section, or this is already also telling you that you can increase, you can have a positive washing, but it's not recommended. So we leave it constant, but this is already a good distribution. Maybe another section can be better, so something at 2 and 4, you can proceed as we did for the case, as we did for the rectangular wind. But this is the principle, the idea. As you look at the efficiency, what I mentioned that sometimes due to some numerical problems, here will be larger than 1, but this is telling you that it's a good efficiency. And also important to point out that regarding how to control this method, because this is a nonlinear method, it is iterated. So as you go into analysis, advanced settings, here you have the options for the LLT and the VLN. So see that in the LLT, by default, you have 20 stations, 10 by wind. So probably it's a good idea to use 40. Okay, it's a little bit larger. And you have your solution, more stations. And look at that, you increase the number of stations, but you have problem with the convergence. So this is the problem here that you have to be careful. That is, you increase the stations, also recommended to increase here relaxation factor. So let me put this to 50, analyze. There are still some points on converge. So the advanced settings, and also increase this one to 1000. Okay, so now everything converged, but see that the result is not very good. Actually, by increasing the number of panels, it didn't have an effect. So sometimes you get into these problems. It can be tricky. So usually this one we increase, and let's see what happened now. No, it's not. Okay, it crashed. Let's just see that. So it wasn't a good selection. So I don't recommend, or if you play with this one, with that, be careful that you can add some instability in your solution. So use the default values. So you can play a little bit, but if you see that you don't get anything, reset and you go to the default values. Appears that it crashed again. So now that problem, I have no idea what could be. And reopen again. Here, text 2. Okay, let me save. Analysis, advanced setting, reset everything, and define analysis, everything here, save. Okay, save, analyze. Okay, now it's okay. So time happens. Be very careful. So for instance, coming back to this, something that you can do as well, you can probably, we change this one, we can change also the core in that section. So you see that everything will have an effect there. And let me go define current plane. I can edit this one. So in this core, let me modify this one. Let me put it to 1, that specific core. So I increase that core. And see what is happening is this one. So kind of, I'm constructing a wind now that it will be similar to an elliptical one just by adding sections. So let's see what happens with this. Increasing the core there, and I select this one, and see that have a positive effect. Now it's getting closer, and this is the point that if I add another section and then increase a little bit the core, I can get very close to that ideal wind. So this is the local lift and the CL. Important here, you can see your stall progression. So remember that the wind here, you don't want these values at the tops to be larger than the internal ones. Okay, that means that it will stall first. So see here that it's stalling first here because it's a larger CL, and then after will stall here. So let me go back to the original wind here. So not actually, let me erase the twist. Okay, no twist here, no twist here. Let me erase this section, save, okay, and let's analyze this one. And let's look at the CL. So this is what happens with a pure taper wind. We saw that one in the review, also the theory, that is more loaded towards the tip when we look at the CL. So remember that when it comes to CL, to have something closer to elliptical distribution, you have a uniform, you want a uniform lift distribution. And if you look at the lift, you want something that is elliptical. Okay, so you can use CL to control the stall progression, and lift, you can use it to control now the ideal distribution. So see here that this is not very good because you are stalling first towards the tips, and that is not ideal. So how do we control this? We need to reduce the CL max, and that is controlled simple by aerodynamic twist or aerodynamic or geometric twist. This is one in this case, or because we already have the data, let's add only the geometric twist. Okay, so as we did previously, you go back, plane, edit here. So the easiest way is that making this negative in the tip. So let me put here twist -1. So I'm reducing now the angle of attack there, and see, let's see the effect just by adding -1. See that we have a strong effect in CL. See that now it's not stalling there. Just 1 degree is enough to control the stall progression. And if we look at the lift, it's not so pretty. So now probably we need to control a little bit. So here I think ideally we can add 3 more stations, 2, 3, and 4. And there we play with the angle to control that. Just to show you, let me add 1 and 2. Define, you edit your wind, and insert after. Yeah, in the middle is okay. So the other twist, and that one's okay, and this one, let's see what happens. Nothing happens because we left there the linear interpolation. Okay, so now we can, for instance, was 2.5, we can increase that incidence angle. So let me go here instead, edit wind, and let me put it at 0. Let me show you, for instance, if I put it larger than, so this is washing, so it's possible, it's doable, but not recommended. And actually it's giving convergence problems, and it was crashing that specific case. And I didn't save. So very important, every now and then save everything. So bum bum bam bam. Let me go. And oh no, actually it's this one. Well, pretty much the same. And okay, so we go like this just to show you 0, and I put it this one -1, and this one was 2.5 in the middle. Okay, so pretty much the same. Okay, let me save. If I run here, okay, and analysis probably have something. Okay, and 0 degrees. So see that is too low. Okay, no, this is the induced CL. This is okay. So see that now here it's not stalling. Probably will stall first in this region. And our lift distribution, we can play a little bit. So as you go back here, can edit the wind, and see that you can add more sections or play here. So for instance, I might here, it will be tempted to increase this to 1. So see that we're having this. Okay, save, put, analyze, 0, and there you go. And probably now you can do something in 3, and you get closer. So I recommend you to go. Do not use washing. It can give you problems. You see here that is crashing, but it can give you problems. So I recommend you just play with the core, wash out, also the aerodynamic twist. But this is how you proceed to design your wind. So look at always at the polar, define your target quantity. In the homework you will have the problem definition, you will have the target velocity, weight. So you will need to do this manual iteration, and that's all. So see that the very positive effect of this tapered wind is the moment. Okay, so there you require less train to keep your airplane balance. So I think I know. So just to show you also the other solvers. So we're using the LLT. Remember, the LLT used all these viscous corrections. So if you define another analysis here, you can get access to different solvers. See that now here you have the 3D panels. I don't recall. Actually, yeah, I think in the newest version, which is this one, the 3D panels, it was able to use 3D panels with multiple surfaces, but it seems that it's not possible because when we added detail, it wasn't enabled. I think that is strange. But let's say that I want to run the VLN. I don't want the viscous correction, so all that data that we have in 2D, we are not using that. And you can run analyze. And this is it. This is your solution. Okay, so there are some differences, as you should expect, but very similar. Okay, remember that here you we don't have CD0, so this is just induced drag. You see here. And for instance, we can use another method, another analysis. So you have the other methods, the rim vortex. As you run your analysis, pretty much the same results. And then you have the other method, the panel method, that probably will be the most accurate one. And all this method lets you use this correction, okay, that you are taking the airfoil data. If you disable this one, you don't care, you don't need that airfoil data. We enable the panel method and you can run. And there you go, you have your results, you hide this one and this one, okay, and voila. LLT, panel, no, vortex lateral, panel, LLT. So there are different small differences because of the formulation, but they are all there around the ballpark. Okay, it's about 10%, 5%. Finally, what I want to show you is you go back to the airplane here. So this is the actual paneling that you are resolving when you use the panel solver in BSX. See there. If you want to change the paneling, here is not recommended, as I say, put in a million panels. There is no need. Okay, so some stuff like this proposed automatically is okay. So that is, you can modify that is you go to your wind definition. What you see here is your paneling. So for instance, let me put in here 30. Save, okay, and see that you have 30 panels there. And this option represents the distribution. Okay, I want a uniform distribution there. You have it there. So it is recommended to have more panels towards the leading edge and trailing edge. So that one you can leave it enabled. But in this case, see that this, I don't need it. So this might be sources of error. So this one I don't need it. I want it uniform. So you go back. So this one you can leave it. And we want, okay, this one uniform and uniform. And see that you have this. Okay, much better. And let me change here 30 also, and 20 and 20. Okay, so more panels not necessarily means better mesh, but this shouldn't have, should improve maybe. It will be slower, okay? Remember that each panel, you add your vortex there, and then you are going to assemble that matrix of influence, and you are going to compute the influence of this panel in every single panel that you have, and so on. So you need to move every panel. So adding too many of them is very expensive because the matrix that you need to solve to inverse will become larger. So at this point, analyze. you're going to see the influence that is much slower. See, that's telling you, and this is where you are putting all the computational effort. Constructing that is not that difficult. All your computational effort is going there in inverting that matrix. So it wasn't that big, and actually 30 by 30, there are not many panels, and it's taking a long time. So let's wait a little bit. Okay, see that this is the number of panels that we have. So that is not that much, but it's taking a long time. It needs to compute all that matrix of influence, everything. Okay, so it is done. We have results. See that now we resolve the actual thickness and everything. It's not like in the vortex lattice that is only the camber line. We're resolving everything. Again, you can put your streamlines there if you like those colors. Let me save also. Put in 0. And you have there. So this is giving problems now. It's not resolving now the wind vortex. And let's look here. We have it there, and if we compare, so as you see, there are very different results, and here we're having problems with accuracy. So adding too many panels can be critical, but also how you choose the clustering. So try to use, when you go there, try to use the default values. Same will happen if I go here and BLN also will use that same paneling. See that it's time consuming, it's less time consuming because it's only you are computing now in the camber line, but it still is an expensive computation. All your angles, and you have it there. So there are very different results. I will trust more in the vortex lattice, in the BLM method. Tends to be more reliable. And here you go. You have it 2 different methods as you go here in the airplane. And let me show you that the vortex lattice, what is solving, see that is the camber line. You have the airfoil definition and will compute the camber line. That is what is resolving. Instead, your panel method is resolving the whole stuff. Personally speaking, I prefer the vortex lattice. They are very robust, and you can use it for everything, for a complete definition of the airplane, tail, empennage, fuselage, everything. Instead, panel method will have limitations. The LLT, as formulated in here in this software, it's only for the main wing, but you can correct it. Now, if you have tail, you just need to add that downwash. Also, let me show you something, another case that in the files that you have, for instance, you can add winglets. Remember, LLT is just the planar wing. It's the one winglet you use, the BLN or the panel method. So as you go in the cases that I gave you, you will find this geometry, rectangular tapered, like if I will recall. So you have a few cases there. Let me open to see which one. No, watch out. So here you have, in that one, you have an example. This is a compound wing. Okay, so you have rectangular and then tapered, and you can follow that. But I have a case somewhere that I added the winglet. Adding the winglet, probably is this. So, no. And civils, yes. Okay, no. Okay, let me show you. Yeah, probably you didn't have the case. I have it somewhere else. So if I go here and this one, I think if I will recall is this one. Okay, here you go. So this is what I wanted to show you, this particular case with winglet. So you have the geometry definition and you add winglets. To add the winglets, it's relative easy. You go in the wind definition, okay, edit wind, and basically you have a new section. So this is your wind, that's from 0 to 6, and then the winglet is this, and you add the dihedral angle. So see, that's 50 degrees represents. You put it this 0, you go there. So you control your winglet here. So it's relatively easy, and you can add different sections. It's up to you. So if you are adding these winglets, remember that the LLT method doesn't. Okay, the winglets, you are not going to see the effect of winglets on your polars. You need to use any of the other methods, okay, vortex, lattice, vertex, or 2D panels. I prefer this one, so you use this one, run in visit, and analyze, compute it for everything, and we should have the polars now. You go here, and you should have your winglet polar. Let me hide everything. Okay, here. So you cannot then run with no winglet. So okay, let me show. So see the influence. So the winglets have this influence here. So let me see what happened. Okay, the winglet reduce. Well, it should be this one that I should compare. Okay, so it adding winglet have an effect if increasing lift. Okay, it will increase the drag because you're increasing lift, and remember that induced drag is a byproduct of lift, but you are increasing lift because you are modifying effectively the lift distribution. So kind of this is the effect of the winglets. You are modifying there. So as you compare with the other with no winglets, see what happens. So pretty much same wind definition, you have this. But probably still studying winglets. It is better in using a proper CFD, but you can see the effect here. So kind of it is modifying this distribution here. In the other case, see that remains here. You put that wall, and that wall will increase that here. But maybe here you will need to control a little bit better that. So that's all. So as you think, all these videos, I was supposed to do some short videos, but extended a lot. I'm really passionate about this field. Now you do aerodynamics, and then you link it to the stability. It's very interesting. So you have there now all the steps to design the wind. The next time we meet, we're going to review this, but that's all. Thank you for your attention. See you next time. Bye.